everyone, welcome back to Mathematical Statistics. We have been talking about the Rao-Blackwell theorem. We have stated and proved it, and today we're going to use it, and this is just another step on our quest for the UMVU, the uniformly minimum variance unbiased estimator, the greatest estimator in all the land. So let's get right to it. I want to remind you what the Rao-Blackwell theorem is, and then we're going to try to apply it. So this is a variance reduction technique for estimators. And so what we have in our setup is some x1 through xn that are probably IID, but more generally have some joint PDF, f of the vector x and theta. And then we have a desire to estimate some function of theta, which could be theta itself, but more generally, a function tau of theta. And to use the Rao-Blackwell theorem, the setup is that we have two things. One is an unbiased estimator of tau of theta, and we're going to call it t. So this is some function t of x, and again, this is unbiased for tau of theta, and yes, you could call it tau of theta hat. But another thing we're assumed to have here is a sufficient statistic. So this is a statistic that sort of condenses the information from the sample. And once you're given that sufficient statistic, you get no more information about the unknown parameter theta from the sample. So I'm going to call this S, and this is its own function of the data. So the Rao-Blackwell theorem says that we can compute T star as the expected value of T given S, and that this is still unbiased for tau of theta, and it has lower variance than the estimator T did. And it will be strictly lower variance if you, in fact, have made a change by doing this Rao-Blackwell computation. So either your estimator is going to remain the same or it's going to get better. Let's try it. Let's look at the Poisson distribution. So suppose I have x1 through xn, IID, Poisson, with parameter lambda. Since we don't use this often, let me remind you that the PDF or PMF, because it's discrete, is f of x. Now the parameter is usually called lambda, and this is e to the minus lambda, lambda to the x over x factorial, and an indicator that says that x takes on values in the non-negative integers. And the expected value for one of these or all of these is lambda, and the variance is also lambda. So the question here is, I want us to find an unbiased estimator for tau of lambda, this particular function. It's going to be e to the negative lambda. And fair warning, before we start, we're going to start something and it's not going to work, and then we're going to start over. So this is going to be a little bit meandering as we discover what maybe we should do and rule out things that we thought we should do, and let's just do it. Okay, so for a solution here, we know because the mean is lambda, we know that x bar is an unbiased estimator for the mean lambda. And we know that unbiasedness does not go through nonlinear functions very nicely, but we have sort of typically tried things that you could sort of find believable here and then adjusted them. So in other words, we might want to try looking at e to the negative x bar. Now the expected value of that is not e to the negative expected value of x bar. So there's no reason to think that's going to work other than it seems like a reasonable start, and let's see what we can do with it. Okay, so is this an unbiased estimator for e to the minus lambda? How can you compute this expectation? You can do it many ways. I am going to first write this as e to the minus 1 over n, the sum of the x's. And the reason I'm doing that is because the sum of the x's is a random variable that also takes on values in the non-negative integers. And we know that the sum of Poissons is Poisson. So if not, you can use moment generating functions to show that. And this sum, although I haven't put the subscripts and superscripts in there because it's a little messy, is a sum of NIID Poisson random variables. So I'm going to write this as e to the minus 1 over n s. This is not a sufficient statistic necessarily, but it's just s for like a sum. And s here is going to have a Poisson distribution with parameter n and lambda. Again, you can show that with moment generating functions quite quickly. Easily, quickly, I don't know. I don't know what your opinion is going to be about it, but it's not bad. Okay, so I am trying to figure out right now the expected value of e to the minus x bar because I want to see if it's e to the negative lambda or maybe something close that we can then adjust because ultimately we want an unbiased estimator for e to the negative lambda. So let's rewrite this as the expected value of e to the minus 1 over n s. And note that this is like, the expected value of e to the tx. It's a moment generating function. This is the moment generating function for s evaluated at negative 1 over n. And yes, it does make sense to have negatives in moment generating functions. In fact, all moment generating functions should be defined in some neighborhood of zero. So you need to be able to go above zero and below zero a little bit in either direction. So if you want to check out let's go to the table and we could do this from scratch. I don't know if we may have already done this, but I'm going to go to the discrete side of our table of distributions. On the discrete side, I'm going to go to the Poisson distribution and then all the way over to this column, the moment generating function. It's already got an arrow on it. It's just that important. So the moment generating function for a Poisson random variable with parameter lambda is e to the lambda times e to the t minus 1. And that's what we are going to use, except we're working with a Poisson with parameter n lambda. So before continuing this, let me just put this moment generating function sort of on the side here. Because S has this Poisson n lambda distribution, this is going to be e to the n lambda times e to the t minus 1. And there's actually no restrictions on t here because sometimes, this was an expectation and the expectation could blow up for certain t, but this one holds for all t. So I'm just going to finish this. So let me recap this. So we get the expected value of e to the negative x bar is the moment generating function of the sum of Poissons evaluated at minus 1 over n, and I just wrote that down here, so let's plug that in. This is e to the n lambda, e to the negative 1 over n minus 1, and that's looking pretty weird. I don't think we're going to be able to massage this into something where ultimately we get e to the minus lambda, like multiply by something, or it's pretty bad. It's pretty bad given that this is what we're going for. So it was an okay idea, right? Because the sample mean is an unbiased estimator for lambda, and we wanted an unbiased estimator for e to the minus lambda. So we tried e to the minus x, knowing that it likely wasn't going to work, but hoping that it would be something nice that we could work with. But it didn't. So back to square one. Still in the same example, the thing we're trying to estimate is tau of lambda equals e to the negative lambda. And we have a Poisson distribution. I did recap the PDF or PMF for you. The probability that a Poisson random variable equals x is e to the negative lambda, lambda to the x over x factorial, and an indicator that says that x can take on any non-negative integer value. And look here. Look at that. It appears that we can get our tau of lambda, which is e to the negative lambda, as the probability that x equals 0. What is x? I don't really have an x here, so let me go back in and call this x1. By x, I just meant a generic Poisson, but let's work with the data we have. So let's just look at x1 or x5 or whatever. You may recall that the expected value of an indicator of an event is always equal to the probability the event happens. So let me remind you that the expected value of the indicator that says that x1 equals 0, even if x1 was continuous, which is not here, this indicator is a discrete random variable. So you'll get 0 times the probability the indicator is 0 plus 1 times the probability the indicator is 1. And we end up with the probability the indicator is 1. But how does this indicator become 1? It is 1 if and only if the event being indicated happens. So this is the same thing as saying that x1 needs to be 0. So this is our target for estimation. We noted it was equal to this, and an indicator has expectation equal to the probability of the thing being indicated. So what we have found is right in here, we took an expectation and we got e to the minus lambda. We have found an unbiased estimator for e to the minus lambda. So let me write that down. An unbiased estimator for tau of lambda, our target, which is e to the minus lambda, is given by the statistic t, which is defined to be this indicator. So what was the goal here? The goal was to find an unbiased estimator, and I guess we're done. So if I made the mistake of writing that as a homework problem or exam problem, you are done. But what I really want to get at is finding one that is a function of all the data because we're wasting a lot of information. So yes, this is an unbiased estimator for our target function e to the minus lambda. But I would like to get a better one with smaller variance. What is the variance of this, by the way? The variance of t is the variance of this indicator. And the variance of the indicator is the expected value of the indicator squared minus the expected value of the indicator all squared. Now an indicator squared, it's 0 or 1, so this is just the expected value of the indicator. I can drop the squared. And we know these expected values. Not only did we just compute it, but we just talked about how the expected value of an indicator is always the probability of the thing being indicated. So this is the probability that x1 equals 0 minus the probability that x1 equals 0, all squared. And for the Poisson distribution, this is e to the minus lambda minus e to the minus lambda squared, which you can write as e to the minus 2 lambda. Not the whole thing. E to the minus lambda minus e to the minus 2 lambda. That's the variance of our unbiased estimator for e to the minus lambda. You'll note it doesn't depend on n, and why would it? Because we didn't use n pieces of information. But it's not going to get better as n gets larger because we're still ignoring those n minus 1 pieces of information. Let's try to Rao-Blackwellize our estimator to get something that is a function of all of the data and something that has smaller variance than this indicator does. Now, the Rao-Blackwell theorem says we need a sufficient statistic, so I will try the Rao-Blackwell theorem. And to start this, we need a sufficient statistic. And the easiest way to find a sufficient statistic is to use the factorization criterion. So let's look at the PDF again. You don't need to see it again, do you? let's just go straight to the joint PDF. Well, here, I'll sort of recap it in the product. So because the x's are IID, this is a product as I goes from 1 to n of e to the minus lambda, lambda to the xi over xi factorial, and an indicator saying that each xi is in this set of non-negative integers. If we multiply this out, we get e to the minus n lambda, lambda to the sum of the xi over the product as I goes from 1 to n of the xi factorial, and no, that's not the product all factorial, and a product of indicators. So you may recall what we are looking for is a pure x part, or at least no parameter part, and the rest of it. We're looking for something like h of x, which actually could be constant in x, but the point is no theta, and then a function g of s of x, and in this case, not theta, but we have lambda. So this is some function where you have both the data and the parameter, and you look in there and you see how the data appears, like in its own little function. So I'm not going to reorder everything here. Let me just circle some stuff. This would be my h of x because it is the pure x stuff. And then this would be where, I mean, I have pure parameter stuff, but that's not part of the factorization here. It's not relevant at all for finding a sufficient statistic. But this would be the g of s of x and lambda. So we go into that function and we see how the x's appear, and they appear in a sum. So this little s of x here is going to be the sum as I goes from 1 to n of the xi. So by the factorization criterion, we have a sufficient statistic. I'm just going to make this stuff capital, and we're done. This is sufficient for this model. I'm just going to leave it at sufficient. Okay, remember what we were trying to do. We want to estimate tau of lambda equals e to the minus lambda. We have an unbiased estimator given by the indicator that the first x, or use x7, I don't care, they're all IID, but the indicator indicating the event that that x is 0. And we have a sufficient statistic. This is the sum as I goes from 1 to n of the xi. And now I want to use the Rao-Blackwell theorem. I want to compute our new estimator, t star, as the expected value of t given s. And we saw last time that this is going to still be an unbiased estimator for tau of lambda, and it's going to be a function of the sufficient statistic. So it will have information from all of the x's in there because the sufficient statistic is the sum of all of the x's. And it will have smaller variance than t. Likely, because I don't think that somehow the x2 through xn are going to disappear. The only way that t star does not have smaller variance than t is if t star turns out to equal t. So I want to compute this thing, and I personally like to sort of fix the given variable because right now this t star is a random variable. It's its own estimator, it's its own statistic, and that will be a function of s. But I want to consider sort of fixing s. You don't have to do this, but I think it makes things just a little more concrete. What was t? T was the indicator that x1 equals 0, given s equals s. And we have already talked about how to compute a conditional expectation like this. It is just the possible values this can take on times the probability it takes those values on in the conditional universe where s equals s. So in other words, the indicator can take on the value 0, and we multiply that by the probability that the indicator is 0, but we stay in that conditional universe where s equals s, plus 1 times the probability the indicator is 1, and the 0 part disappears, so we get the last line. You don't have to write this, because I think you know what I'm going to do next. The indicator is 1 if and only if x1 is 0. So this is the same thing as like the event that x1 equals 0 happens in the conditional universe where s equals s. So let's compute this. It's a conditional probability, and I am going to go straight for the definition. This is the probability that x1 equals 0, comma, and s equals little s over the probability that s equals little s. This looks a lot like showing something is sufficient from scratch, but it's not quite the same thing. Here we're actually computing something. We're not finding a factorization or finding a PDF or anything like that. So you can assume that this little s is actually a valid s that can be observed. And so all your indicators are going to be turned on. They're all going to be 1, and we don't need to write them. But let me go back up to the circle and say, for any little s in the non-negative integers, the following computation is going to hold. I would love to split that numerator apart, but remember, s is the sum from 1 to n of all of the xi, so there's an x1 in there, and this x1 over here means that the two things on both sides of the comma, these are dependent random variables. In order to make them, kind of pull them apart, I can write this as the probability that x1 equals 0, and then the sum as I goes from 2, so I'm changing that up, to n of the xi, that part needs to be the remaining s minus 0. Now you don't need to write that 0, but this is just to tell you what would happen if there was like a 3 over here. Then x2 through xn, if all of the x's up through n have to sum up to s, and x1 is, say, 3, then x2 through xn has to sum up to s minus 3, so that they totally sum up to s. So I'm just putting this 0 in here so you can maybe see what happened. I don't know if that's helpful or not. And the probability that s equals s. So now on top, I've got an x1 and I've got everything but x1. And x1 is independent of x2 through xn, so we can use independence and write this as the probability that x1 is 0 times the probability. I don't want to give it a name, but I won't. And in the denominator, I could write that out with the sum as well. That is the full sum starting from 1, but I think I'll just leave it. Let's fill in the probabilities. The probability that x1 equals 0 is e to the negative lambda, and you can stop there if you're fine with that, but just to see where everything comes from, there's the Poisson PDF. And I'm not going to write the indicator because, you can write it as like times 1 because we're plugging in 0, and 0 is in the appropriate set. Let me go to the denominator next. This s has, as we've seen, a Poisson distribution with parameter n lambda. I'm assuming that s is in the right space. So this is just going to be e to the minus n lambda to the s over s factorial. And because we're assuming that s is in the right space, I don't need to write the indicator. It would be like multiplying by 1 because s is, in fact, in that set of the non-negative integers. Finally, this is going to help us do this other term up here. This is just a Poisson random variable, not the whole thing, the random variable part. So this is Poisson with parameter n minus 1 lambda because it's a sum of only n minus 1 independent Poisson random variables. So right here, I'm just going to get what I have in the denominator with all of the n's replaced with n minus 1. So e to the minus n minus 1 lambda, n minus 1 lambda to the s over s factorial. And again, I told you why we didn't use the indicators. We're not trying to find a PDF as we usually are, or show a PDF factors. We're actually evaluating it at a number where s is in the non-negative integers. So all the indicators are 1, and I'm not writing them. As a reminder, what is this? This is the expected value of t given s equals little s. And we can get a lot of simplification out of this. For example, all of the e's are going to cancel. The s factorials are going to cancel. I need another color that you could see. I don't know if you could see this. This lambda to the 0 is 1. I've got a lambda to the s here and a lambda to the s here. So those two blue circles are going to cancel. And the only thing we are left with is n minus 1 over n to the lowercase s power. Again, this is this expectation of our unbiased estimator t conditioned on knowing the sufficient statistic, but ultimately what we want to return is this, where we have not fixed this value. But I did that to make the computation a little more straightforward, I think. But all we have to do to come up with the final estimator here, our t star, is the expected value of t given capital S. In other words, it hasn't been given to be a little s. So it's going to be n minus 1 over n to the capital S. And I think it's good form. I mean, if you have this as your answer on your homework and you have defined S up above, that's fine. But I think it's kind of good form to give your estimators in terms of the original X's. Here is an unbiased estimator of e to the minus lambda. And now it's a function of all of the data. And we can compute the variance here, and we'll see that the variance is smaller. Now we know that's true because we proved that, but just as an exercise, we did compute the variance of t. So what is the variance of t star? All of the randomness is up here, and it is in a nice clump. So I don't have to compute expectations with respect to the joint PDF for all the x's. Note that t star is a constant. Yeah, it changes in n, but by constant I mean non-random. So I'm just going to fix n and say it's a constant called c to the s power. The variance, well, you already know we're going to need the expected value of t star, and that is the expected value of c to the s. And what is this? I don't have an e there anymore like I did before. Now, technically, you could do the following. It's actually not going to be that bad to do, but you could say, okay, well, s takes on values from 0 to infinity, so I can put c to the s in front of the PDF for the Poisson with parameter n lambda. And this is not bad at all to do. You can pull this in with this one exponent and rewrite this as a Poisson PDF by putting in and pulling out certain constants, and then knowing that the Poisson PDF sums to 1. So you can do the integrating without integrating or summing without summing trick. I think I'm going to use moment generating functions again. So the expected value of t star is the expected value of c to the s, and I don't have an e. So how can I use moment generating functions? I could write this as the expected value of e to the log of c to the s. I could write it as the log of e as well, but I wanted the e down there on the baseline because I want it to look like a moment generating function. But it doesn't. I would like to see the expected value of e to some t times s. But remember, if you have an exponent on your log, you can bring that down in front. So this is the expected value of e. I'm going to rewrite it like log c. I'll put the s over here. So this is the moment generating function for the Poisson random variable with parameter n times lambda evaluated at the natural log of c. So this is e to the n lambda, and then we had e to the t minus 1, so this is going to be e to the log of c minus 1. And we can get some simplification here. We've got e to the log of c, so e to the n lambda c minus 1. And remember, c was n minus 1 over n. So I'm not going to bother to rewrite the whole thing to do the expectation squared. Let me cheat a little here. If you want the expected value of this squared, that is the expected value of this squared, and that is the expected value of c to the 2s. So let's bring that 2 along for the ride. There'd be a 2 here, and a 2 here, and a 2 here, and a 2 here, which would then pop up here. So we'd get e to the log of c squared. And so, what a mess. Let me just clear this out. The expected value of t star, let me recap, that was e to the n lambda c minus 1. And the expected value of t star squared is going to be e to the n lambda c squared minus 1. Hopefully that made sense. I went through the squared pretty fast, but you can go through it in slow motion, and I think you'll get there as well. Okay, so what is the variance? The variance of our Rao-Blackwellized result is the expected value of t squared minus the expected value of t quantity squared, which means that you can multiply the exponents, and you get e to the 2n lambda c minus 1. That is not all that nice looking, especially if I want to compare it to the other one. Um, because this is just algebra, maybe I'll move on. But at this point, you should put in the constant. Like you'll have to square it out, and you could subtract 1. You'd have like n minus 1 squared over n squared minus 1, which should be n squared minus 2. I'm just doing it, aren't I? Minus n squared over n squared. I think this will actually simplify down kind of nicely. And when you're done here with this computation, you won't have an n squared. Yes, you will. Never mind. I still think this will simplify kind of nicely and into something that you can compare with our other estimator's variance. Okay, that was a cop-out, but I need to do this computation again later for something anyway, so we'll eventually do it. It's just algebra. Our first Rao-Blackwellization. Next up, in our pursuit of the umvu, is a concept of a complete statistic. I am fairly certain that when I write down the definition of a complete statistic here, it's going to look strange and unmotivated, but I hope to convince you that it's an important thing, and I think you're going to like it ultimately. So the definition of a complete statistic. We have some sort of model, meaning x1 through xn, probably IID, but with joint PDF f of the vector x and theta, and a statistic, capital S. I know what you're thinking. Why aren't you calling it capital C since you used S for sufficient? You could. Capital C as a statistic just doesn't do it for me. But it's a statistic, so I'm using an S. You can use a T, whatever. But this is some function of the data is complete for the model, or just like everything we've talked about with sufficiency, complete for estimating theta or estimating a function of theta. If for any function g, and we'll talk about the dimensions and where this is going in a moment. Let me just write it as a function g, such that the expected value of g of s, the complete statistic, is 0 for all theta in the parameter space, we must have that g of this capital S is 0 with probability 1. So, is it your new favorite definition? It's bizarre looking at first, but it's really useful, and let me try to convince you why. So before I try to convince you of that you care about complete statistics, let's look at an example. Let's do a discrete example, and let's keep it as simple as possible because complete statistic computations get bad pretty quickly. Suppose we have IID Bernoulli random variables with some parameter p. I haven't told you yet how to potentially find a complete statistic, but I'm going to give you one just like we started with sufficiency. Let's show that the statistic S, which is the sum of the xi as I goes from 1 to n, is complete for the Bernoulli distribution, for estimating p, for estimating any function of p, or for the model, just to wrap that all together in a pretty bow. Okay, what does this mean? Oh, I forgot to talk about the dimensionality of G, but we're going to get to see that right now. We're going to suppose we have a function G such that the expected value of G of S equals 0. Now, S in this case is a one-dimensional statistic, and 0 is a one-dimensional number. So I'm talking about a function G from R to R. But more generally, the function G is going to go from RK to R, where K is the dimensionality of the statistic. So maybe it's the sum of the x's, comma, the sum of the x's individually squared, something like that. It's whatever it needs to be in order for you to write this down. And I want this not only to hold like that, I want this to hold for all parameters in the parameter space. The parameter here is P, and that's between 0 and 1 inclusive. So that's a whole lot of P's there. And what is this? Now, I don't know what G is. I just know it's a function that satisfies this expectation being 0. So let's write out this expectation. I don't need to deal with the joint PDF of all the Bernoullis because S, as the sum of n IID Bernoullis, we know has a binomial distribution with parameters n and p, and if not, check out moment generating functions. It's easy to show that way. So we get 0 as the expected value of g of s, and this is going to be the sum as s goes from 0 to n. That's where you get to go with a binomial np. Remember, the individual x's are zeros and ones, so when you sum them up, you could get 0, you can get n, or anything in between, any integer in between. I'm going to get g of little s times the probability that s equals little s. And in there, I'm going to plug the binomial probability. So 0 to n, g of little s, n choose s, p to the s, 1 minus p to the n minus s. This whole thing is supposed to be 0. Let me recap that over here and say for all p between 0 and 1. Okay, this is a polynomial in P of degree less than or degree less than or equal to n. Like it looks like a polynomial of degree n, but maybe this is 0 in some places, so maybe not. But at least n and no more. Polynomials of degree n can have at most n zeros, that is, at most n values of p that you can plug in to make this expression evaluate to 0. But we're saying we can plug in an uncountably many number of p's and get a 0. So the coefficients of this polynomial, because no matter what I plug in, I'm going to get a 0, and that's way more than n different values, all the coefficients here have to be 0. So this is a little messy in general. We could do it, but let's just look at a case where n equals 2. Let me write out this polynomial. So we've got g of 0, n choose 0, p to the 0, 1 minus p squared, plus g of 1, n choose 1, p to the 1, 1 minus p to the 1, plus g choose 2, n choose 2, not choose 2, g of 2, n choose 2, p to the 2, 1 minus p of 0. So let's try to write this out as a polynomial in p. So we'll have a p squared term, a p term, and then a constant in p. Oh, can I do this off my head? Let me at least multiply this out a little bit. N choose 0 is 1, and then we get 1 minus 2p plus p squared plus n g of 1 p minus p squared plus n choose 2 g of 2 p squared. So let me collect the p squared stuff. Over here, I've got a g of 0. In here, I have a minus n g of 1. And from here, I have an n choose 2 g of 2. And the p terms from over here, I get minus 2g of 0. In here, I get plus n g of 1. I gotta stop using that color. And that is it, I think. If not, you get my point. So let's get the constant term. It looks like right here, g of 0 times 1. So we'll just get a g of 0. And this is 0 for all p between 0 and 1. And that means the coefficients have to be 0 because it can only be 0 in up to 2 places. So this implies, well, this is like an a p squared plus a b p plus c equals 0. And because it's 0 for all p in here, this implies that a is b is c is 0. So working backwards, g of 0 has to be 0. Plugging that in here, this is 0, and this whole coefficient has to be 0, and that's going to imply g of 1 has to be 0. This is 0, and this is 0, but this entire thing has to be 0, and that implies that this has to be 0, and that implies that g of 2 is 0. We're getting a function g that is not necessarily 0 everywhere, but it's 0 on non-negative integers. And in particular, if s is the sum as I goes from 1 to n, or in this example 2, this takes values in. We're summing up two Bernoullis. They're zeros and ones, so we can get 0, 1, or 2. So what we have is that g of capital S is 0 with probability 1. And what that part means is that g can be doing anything else. That's supposed to look. It can be doing anything else like off integers. All right, I don't know why I made it look like that. These are integers, right? It doesn't have to be 0 everywhere, but it has to be 0 for any value this can take on that can go in there. That's what the with probability 1 means, because with probability 1, this number, this random variable is going to be 0, 1, or 2, and therefore g will be 0 when you plug it in, but the function does not have to be identically 0. Okay, let's do a quick continuous example. Hopefully this one will be even quicker. Suppose we have x1 through xn, IID, uniform 0 theta, and we work a lot when estimating theta here. We work a lot with a maximum. We don't have to, but I want to show that the statistic defined to be the maximum is complete for this model, for the uniform distribution. So that means we're going to take any function g such that the expected value of g of s equals 0 for all theta in the parameter space. And the parameter space for uniform 0 theta is all positive theta. We want to show that g of s is 0 with probability 1. So to compute this expectation, we need the PDF for this maximum. I am just going to remind you of what it is. If you need to, you'll find it by first finding the CDF. And this is n over theta to the n x to the n minus 1 on 0 to theta. So that's not the uniform PDF. That is a beta-looking PDF. It's not on 0 to 1. It's on 0 to theta. And it is the PDF for the maximum, which should not be a flat line. Right? If you are collecting values between 0 and theta and you just look at the maximum, and then you do it again and you just look at the maximum, you're going to get values that are more piled up on the right side. So your PDF should have more area over here. All right. So going back to the expectation, g of s, this is going to be the integral from 0 to theta of g of s. So s is the maximum, so I'm going to write that maximum PDF in terms of an s. And what do we have here? We can pull this out, and if this whole thing equals 0, then this implies that 0 to theta g of s, s to the n minus 1 ds must equal 0. Like it's not gone. I didn't cancel it, but let me actually put it in over here. Right, if this is 0, then that means that this part is 0 for all theta greater than 0. So to get at the g function here, I'm going to take the derivative of both sides of this boxed equation with respect to theta. Not this part. I don't care about that anymore. I've sort of ruled that out as something that could make this whole line equal to 0. On the left side, we've got some fundamental theorem of calculus going. This is g of theta to the n minus 1, and on the right side, we still have 0. Now, if this is going to hold for all theta greater than 0, no matter what you put here, this implies that g of theta must equal 0 for all theta greater than 0. And this is an argument. This just implies that, g of s or g of x or whatever letter you want to use is 0 as long as the argument is greater than 0. So this implies that g of the maximum of those uniforms is 0 with probability 1. And again, the with probability 1 comes from the fact that g could be doing anything for negative arguments. But this maximum can only take on positive values, and we do know there that this function has to be equal to 0. So I'm not saying that g of x is completely 0. It could be doing something weird for negative x's, but this is definitely going to be 0 with probability 1, because with probability 1, this only takes on positive values. Okay, how much time do I have? Getting close. With the remaining time, I'd like to convince you of why you care about such weird things as complete statistics. Why? Why do we care? If you are trying to estimate, so suppose we want to estimate some tau of theta. We've got, x1 through xn with some joint PDF. And suppose we have a statistic S that is complete for the underlying distribution. Sorry, I'm rushing a little bit here, so I'm not writing the whole setup, but we've got x1 through xn, maybe IID, maybe not. And suppose we have two functions of S that are unbiased for our target here, tau of theta. I.e., we've got something like the expected value of G1 of S equals tau of theta, and the expected value of like a G2 of S equals tau of theta. Then check this out. You'll get 0 if you take tau of theta minus tau of theta. This is the expected value of G1 of S minus the expected value of G2 of S, and we can pull those expectations together. This is the expected value of G1 of S minus G2 of S, and that is just another function of S, like call it G of S. If this is 0, then if S is complete, this is going to imply that G of S is identically 0, or at least 0 with probability 1. Again, I'm rushing. This only needs to be 0 for all parameters in the parameter space, so I'll pick up with this next time. But just to finish the thought at least, this is G1 of S equals G2 of S, or minus equals 0, so G1 of S equals G2 of S. I was claiming I had two unbiased estimators of tau of theta that were both functions of a complete statistic. That's not possible. They have to be the same. This is going to help us narrow down our search for the umvu. If we are restricting ourselves to looking at functions of complete statistics, and we find a function that's unbiased for the thing we want to estimate, you'll know for sure there's no other way to manipulate that statistic to get a different unbiased estimator. So it's going to be the final step in narrowing things down for us to find the umvu, which we're definitely starting at the beginning next time. So please come back next time on Mathematical Statistics.